And I start sharing my screen. So let's see. The first thing that I want to open is obviously the one that I closed. So okay. So this is like the things that we will discuss today. Now I share. Just zoom. Okay. So now you should see the presentation, Mariam, right?
Yes.
Okay. Good. So, well, today is the 16th of September, and we will continue with our crash course of VASP. The structure, okay, now I'm here. Why? Okay, but no, this is not the way that I want to share this. 1 second. Okay, now, yes. So, today we will talk about the correction of Anson 2. We will discuss about the Python Bash project. So later I will define a bit better what I mean with the word discuss. And then we will go through the exercise of Anson 3. Tomorrow we will have the tutorial for Anson 3. And then next week, right before Santa Tecla, we will finish everything, okay? So next week we will go with the correction of exercise 3, and then we introduce Anson 4, then tutorial of Anson 4, and then the very last day on Wednesday 22nd, yeah, here there is a mistake, we will go with the correction of exercise. So as always, the materials are available on OneDrive. Today, I already upload also this presentation, so you will not have to wait for me till the afternoon. And yeah, like I'm registering, so the standard things. Okay, so I'm recording and everything will be online, and then you have the last manual, nothing there. So today, I will start with few tips about like the work in general and also about a PhD, or at least what I found useful in my PhD. The only problem is that I realized these points quite late, like in the third year. But since you're just, some of you are just starting, I think it's better like to start getting it, and they are kind of general. I mean, like they apply to experiments, theory, whatever, you know. Then we will go through an update about the status of Python and Bash project, and then later I will define why I mention update and not correction. Then we will correct the exercises of the Anson 2, and then we go quickly on lecture 3 and instruction for Anson 3. So today, the lecture 3 will go through two lectures of VASP. One is about the ionic optimization, the other one is about electronic optimization. These are the two slides that are kind of related to Anson 3. I won't discuss this third performance because this is not for you. I mean, this is if you were like the system manager of our lab and you needed to install and compile VASP. We are lucky that Martin does it for us, so there is no point for you to study this, but if you are curious to see how it works, just go and check it. And then the Anson will be about surface optimization and electronic properties, okay? Then, first tips of the day. I have a question for all of you. Do you think that you can walk 1,000 kilometers in general?
No.
How many days?
Yeah, in which period?
Yes.
Which time period?
Okay, so we are entering in the right life point. Exactly, like the question of Enrique, how many days? That's the point. So actually, in my case, for instance, since I'm living close to Parte Alta, I'm doing around 2 kilometers per day, well, per day, per morning when I'm going to execute, so 2 times. So it means that in 1 year, I'm doing even more than 1,000 kilometers. And this very stupid example is just like, you should apply this also in your PhD or research project in general. So like there is, like your project is something like 1,000 kilometers, it's very long. So if you try to run or walk 1,000 kilometers in a day, you will probably die or you will not manage. But if you take it slowly and every day you do a small step, then you will manage for sure at the end of the project. So these are the basic steps. The first things, and this is what we are doing now. So this is all what this Anson is about, is understand properly the basics. And this is very important. Don't try to skip these 3 steps and go right to the end, because what will happen is that you will do a lot of mistakes and you will arrive 2, 3, 4 weeks before the real deadline with nothing done, because whatever you have done so far is wrong. And that is something that we don't want to happen and you don't want to happen. So First, you need to understand properly what we are doing. Take your time. If it takes 2-3 hours, it doesn't matter because you are learning and that takes time. Then after that, when you get a project assigned and that about experiments of theory, this applies about everything, then you need to read properly the state of the art. And trust me, I was very slow in that. I started reading properly the third year of my PhD because before I was lazy, I was like, no. I start submitting. And basically, when I was doing that, I was just losing my time because a lot of results, a lot of things are already there. And there is no reason to repeat simulation just because you want to be fast. It's much more valuable to spend like 2-3 afternoons reading papers of other people and planning what you want to do rather than start running simulation just to run. Because remember what we said the other time. I mean, all the simulation that we run, they are costly. I mean, they require money. There is electricity going. We don't want to waste things. Okay? So read and plan. So after we do the hands-on, or also like in parallel, when you get a project assigned, then you read the state of the art. So you read a lot of paper related, whatever you can find online, you read. Then you plan your simulation carefully. So you say, okay, I want to study this system. These are the structures that I can assess. These are the intermediates that I need to put on top and all these kind of things. And after a lot of time, when you are kind of sure about what you want to do, then you submit simulations and in parallel, you start writing paper. Because remember, you don't need to, I mean, I know that for a lot of people, the problem is like, you're like, okay, but if I don't submit simulation, then I cannot start writing paper. It's not true. Because a paper is, there is also an introduction. And to write the introduction of the paper, you need the state of the art. Because if you don't know the state of the art, you cannot write an introduction of a paper. And then also for the discussion and the conclusion, you need to know what other people did before you. You cannot just say, look, I don't know what happened before me, but I did this. Because the reviewer will complain. So take your time. All this is to say, don't worry. Like if you have 1 month, 3 months, 1 year, 1 life, it doesn't matter. The problem is the same. Take your time. Because if you take your time, then you will get to the end, you will get to the objective, you will get to the 1,000 kilometers. If you start getting there in 1-2 days, you will not manage, okay? Second tip, and this applies to the bash Python script. There is a big difference, and again, it took me a while to understand that, between a master's degree and a PhD degree. During a master, you are learning some knowledge that is already established. So if we are learning like the theory of special relativity by Einstein, is a theory that has been done like more than 100 years ago, is known, is proved. So also exercises related to that are kind of easy because you just need to apply a theory that is there, is fixed, is clear. So here we can talk about correcting exercises because there is already a solution, is already there. A PhD degree, and that applies for everything that is novel, you are looking for a new science. You're looking for something novel. There is no solution. You are looking for a solution. And this, for instance, is your Python bash script. There is no solution. You are looking for the solution. So what I meant about, okay, on Thursday, we will discuss or we will correct whatever I put it, is just about, let's see where you get and let's see if I need to help you. And then if you already managed to solve all of them, good, perfect, nice. But if you didn't, there is no problem because these things require time. Because these bash and Python scripts are not like the hands-on that are already done. It's something new. It's something that you need to try, but it's worth a try. Because in the PhD will be the same. You will get projects that nobody else before you try to solve. And you will need to work about that. It will take time, will be difficult, but you will need to try. And there is no solution. So remember, also like whenever like a supervisor will tell you, look, work on this, what she or he meant is to try to look for solution. It's not like, okay, in 1 week, you bring me solution because there are no solutions. You need to look for that. It can take time. Okay? So after all this big introduction, like the big question is like, how are the projects going? So it's not about, I want to correct your exercises. Today, I just want to have a like brief talk, like, okay, we started, oh, we fixed one of them, oh, and most important, if you have any big problem. So if you are stuck at any stage, then we can quickly discuss today. Okay? So, whoever want to start.
For
Yeah,
example,
you can
okay.
start.
We can talk about our projects. We have worked on the first script, which is the ordering of the.
Sorry, if you need, we can bring our computer.
No. I mean, we can go through that tomorrow properly with the computer, point by point. Today, I just want to get a general overview. Okay? Go ahead.
And yes, we have been able to produce that bash script that orders that. We wanted to improve that, making a counter of the layers, because I think that it's a fixed value in the first example. And my question would be, because I have some lack of knowledge about the cases that script can take. Every case, every postcard input would have the same number of atoms, sorry, in each layer.
No.
Yes. Okay. So
that
that okay.
So for the script, you will need to figure out a way to check how many atoms you have with a fixed Z position.
Yes.
Because whenever you have the same Z position, that is on one layer, and then you need to count them. Or the easiest approach. Yeah, so that is one of the approach, or what you have is the total number of atoms. So since you have the total number of, still you have the total number of atoms.
In order to fix them, if in the example it works when every layer has the same number of atoms, but if not, it is a little bit more complicated and the script can be improved.
Exactly. So I think what you will need to do is to count how many different Z position you have. And that will give you an idea about how many layers you have. Okay. That should be the easiest approach, because the way that the script is done now, as you see, is just taking all the atom, divided the overall number of atom by 2, and freezing the bulk part. But in that case, you need to count how many Z positions you have.
We have been able to introduce a variable, which means the name of layers that you want to fix.
Oh yeah, good.
But it only would work if the number of atoms per layer are the same. Yeah. We need to first count the number of layers, because the script that we have nowadays just works for postcards with four layers. And after that, I think that the next improvement would be that idea to see if it can work for a first layer with 3 atoms, a second layer with 4 atoms. I don't know.
Yes. Okay, one important point, because I think I misunderstood the first part. In general, you should have in principle, let's say you don't have for every structure the same number of atoms per layer, but generally for a given structure, you do have the same number per layer. Okay, so let's say if you have a nickel, usually nickel should have 4 atoms per layer. If you have a copper, that may be 5. If you have copper oxide, can be 6. But for a given structure, should be constant.
Okay, that was my question, because if you want to fix a layer and our layers have 4 atoms, it's easier than if you have to fix just for the first layer 3 positions, for the second layer 4 positions.
But yes, in general, yes, because remember that usually these layers are periodic, repetition of your slab. So if they are periodic, they need to be the same number.
Okay, so we can consider a good script that just considers that every layer is
exactly, because that will apply for 99% of the cases. I mean, you will need to have a very, very bad crystalline structure not to be the same. So so the answer was good.
Okay, so you, Shishan, want to talk about the second script?
I mean, the second we don't have so much problem with the second, just to get the key points. I mean, in the third one, we don't know how to do that, because there is and even we cannot understand what the introduction of the script. And I remember that here is a sentence that said that if we want to put 2 layers, 2 atoms to the cell to the surface, and we just say that we need to sum the the coordination of the two atoms about the surface.
Yeah.
But it's not true.
Yeah, why not? Remember that, like, so the point is that
Because if we need to, so the first part we should do is we need to select an atom from where we need to put the two atoms about. So when we choose that, the coordination, I mean, just the x and y is just we call it fixed.
Yeah.
So, but in the other box, that in other contact, it just have CO molecule.
Yes, exactly.
So in this case, the coordination, the coordination values of this molecular is totally different to this. So first thing I mean just simply the sum it can't work.
You're right. So the point is that, I mean, of course, I didn't go to that because that is also your work. But as you said, you have two different constructs, okay?
Yeah.
One is the structure, one is the CO. The CO has a given position. What you need to do is to, like, put the CO in principle, like, to the origin, so to 0, 0, so that, like, the carbon is at 0 and the oxygen is somewhere. So first you will need to take that carbon, like subtract the coordinate of the carbon so that you have the CO in the origin. Then you can take this coordinate and you put it on the cold card. The problem with that is that then you will have the CO inside the bulk. So at this point you will need to sum the coordinate of your CO to the coordinate of your atom on top of the surface, so that the CO will move there, right in top of your atoms, and then you will also add an offset on the Z, so that the CO is on top, okay? But if you want, like tomorrow, like we can open the script, I can go through the script, so we go step by step, and I also give you some tips how to do it, okay? Because otherwise now I'm talking, I mean now you just have tips, but it's better to go directly on.
So that offset that you were talking in the Z direction, which is the criteria of putting that?
1.5 angstrom, 2 angstrom, like should be
like a rule of thumb.
Yes, yeah. So the point is that, you know, like then this system will be optimized. Just 1 second.
I know.
And so since it's going to be optimized, then VASP will decide the best position.
Yeah.
But the problem is that you still need to keep some distance, because if you just put it on top of the atom, then it will just repel a lot. And if you put it too far, like 5 angstrom, then there will be no interaction. So 2 angstrom is more or less the distance that you have for chemical.
In order to relax after that and optimize it. Okay,
Exactly.
I understand.
Yeah.
Okay. Okay. Because this, I mean, whatever it you will need to know that the distance between the molecular that will be absorbed, so around the surface, because the distance should be it will depends on what metal is it, or if it have just absorbed totally.
Yeah, I understand. But the point is that the distance will be optimized by VASP. So you are just giving an initial guess. So the initial guess of 2 angstrom is okay, because the initial guess can be the same for all the systems. Then VASP will optimize the position of the carbon monoxide where it should be. And that will be indeed different for different type of surfaces. But that initial guess, 2 angstrom is okay. Okay? Then tomorrow we can go directly through the script, so we go, like, we discuss better. Then instead, like Mariam, I already know that, like, we are fighting with, like, the things, like, and then today I will think better, like, to see if we can fix it. And then I also talk already to Santiago this morning. And you already have all the libraries, so there is no problem. Is there anything, like, apart from Mariam, because we need to fix it, I'm already aware of that. Do we need to discuss anything, Santiago, in principle?
Just 5 minutes before we started this lecture, Albert proposed me another option in order to make Mariam use Python. This, she could maybe connect to, I don't know, my ICIT workstation via AnyDesk. Since I can work with my personal laptop, and she can use my my Anaconda installation in my ICIQ workstation, so that in theory, potentially she should not have potential problems with the Python installation of Anaconda. I don't know. Maybe we can try today, Mariam. I don't know if you have time.
Yeah, sure. We can talk about it later together. It's okay for me.
Yeah, that should work.
It should work.
So also now she doesn't have firewall anymore, so there should be any shouldn't be blocked. So it makes sense.
Okay then. Sure.
Yeah, nice. Yeah, Albert is giving very nice suggestion. Nice. We need to offer a beer to Albert then. Good. So nice. So yeah, today this afternoon you can talk, Mariam and Santiago. Nice. So yeah, so I think we can continue now. So we can go very quickly on the answer too. So the first question that I had for you is what is the most stable crystal structure of silicon, and does your prediction agree with experiments? So if you remember, we had 3 crystalline structure that you were assessing. One was the FCC, one was the diamond FCC, the third one was the beta T crystal structure. Do you have any idea of what is the most stable one, or what is the one that we should find in reality, let's say?
The diamond one.
The diamond. Why?
Because the minimal energy.
Exactly. So you see here that you have 2 atoms per unit cell for any of the 3 systems. You see that the energy, the lowest energy is the one for diamond. So that means that this diamond silicon is the lowest energy configuration. So it's the one that you will find in reality, let's say, in experiment. And actually you see also Wikipedia that experimental is that one. So that means that with VASP, we got to define properly the structure. Then second question, from the density of state, do you consider silicon and nickel metals or semiconductors? Motivate the answer. So silicon, metal, semiconductor, insulator.
Silicon semiconductor.
Semiconductor.
Yeah.
Why you say that it's a semiconductor based on DFT? I know that experimental.
Yeah, I know the bands. You can't find the bands energy of the energy of bands. Because there's from the 2 the bands that the active X the ground energy part, and another part is excited states. There's a space between them.
Exactly.
And the Fermi.
I mean, so for a semiconductor, the Fermi level will be in between the valence band and the conduction band.
And for nickel and for nickel, I think it is continued.
Exactly.
From them, there is
exactly. So how you could see that? So here, this is the density of state, and this is the Venn diagrams. This is for diamond silicon. This is for FCC nickel. I know that is very small. So you see that here for diamond silicon, you see that there is a band gap, as Sichen just said, while for nickel, this is continuous. And so for theory, in a metal, let's say you don't talk about valence band and conduction band because they just overlap. And let's say you have electrons till your Fermi energy. Instead, for a semiconductor, you have a band gap. So that means that your occupied states are here. So you can have electron here, but you don't have electron in the conduction band. Then you can dope your semiconductor, you can charge it, so you can do something so that some of these electrons go up. But you need to have a band gap, and you see the band gap here. So that seems, well, that say that then silicon is a semiconductor. And in case this band gap is very large, then that is an insulator, because it's even more difficult for the electron to move from this valence band to the conduction band. Okay? So that was the easiest way to define it. Important point, in VASP, the estimation of the band gap is always bad, in the sense that you can get an estimation of how much the band gap is, but is always an underestimation. So that means that if the experimental band gap should be 3 electron volts, with VASP, with standard PBE, so the one that we are using, you will find a 0.5 electron. And here you will need to do hybrid-like simulation, but I mean, it's not that important now. What is important is that VASP can reproduce the different like electronic properties. So can tell you, look, this is a semiconductor, this is a metal, but it fails if you want to have a proper estimation of the band. Okay? So in case you wanted to say exactly how much should be the band gap for silicon, standard PBE will fail because we'll give you a number that is not the proper. Okay? Good. Then, yeah, then we are already ready for answer 3.
Can I ask a small question? We were talking with Santiago that we don't remember when you go on Python for View, how to see that band structure. Because we have been able to take questions.
But we were not able to
Okay, so I'll quickly do that now. So let me just.
How to say that? Band.
The band structure, yes. The left part of each of the.
I mean the name, the professional name.
No, that is, you can talk like band structure or band diagram.
Oh.
Like there are different ways. Okay, good. So now I should have it. So let's take, for instance, now I will also share it. Can you see that if we look here? Okay, yeah, for instance, let's go to the diamond. Okay. Okay, so now I open a terminal. I enter like on diamond DOS. Then, as you already know, you do Python for VASP run. This open like the Python for VASP interface. And as you see, you go to electronic and you need to click. If you click on DOS plus band, it's okay. And then you go to show. You see like you have DOS. You have DOS x-axis. And then you have, for instance, like DOS and band. Okay. So you need to go to show. And if you want, you can also go then to graph, export, and you can, for instance, like save it as like either as a PDF or like the raw data. So for instance, if I do like, let's say if I go to my desktop and then I save it as like band, I save it as a PDF, export. Now you will see that if I open my desktop, if I open my desktop, basically I will see what I just printed, okay? So you can also like get them as a PDF or raw data. And you can play with all these, like I didn't discover yet all the things, but there are many things. Like for instance, you can also see like inverse participation ratio that I don't know even what it is. Then you can see like, the band alone. Yeah, you can play, there are a lot of things to play with, you know, because for instance, you can also like, this will be later. There is also a way, for instance, to get the STM if you want, like this Python for VASP is good. Okay, good. So I think that was clear now. No worry. Then, okay, so we can start with what I want to discuss today. So, first things that we will go through is this ionic optimization. Again, I will do as the last week, in the sense that what will happen is that I will focus on like the most important like concept, and the one that I don't think is that important, I will quickly like pass through that. Okay, so this formalism that we will introduce today is just to explain you more or less the different hybrid that you can use. So if you remember, like there are two different things that we are doing in a VASP simulation, and probably I can show you on a terminal quickly, because then you see. So if I go, for instance, to a standard like optimization, like the other time. Okay. Okay, but I need to open. Okay, so no, this one is not, sorry. Okay, this one. Yes. Excellent. Now, view, zoom in, zoom in. Okay, so no, it's not this window, it is this way. So if you see a standard like VASP optimization, as we said the other time, you see like 3 ionic steps, 1, 2, 3, and inside them you see some electronic steps. This presentation that I'm showing now, like discuss how these ionic steps are calculated. So ionic steps means that you are moving your ions, so that you are moving the central atoms, okay? While all these steps in between, this one, are about electronic convergence. So how the electrons are moving, so how the electronic structure is converging within a given ionic step. So what VASP does is that we start with a given structure, optimize the electronic configuration. When the electronic configuration is optimized, give you an energy. Then, that is this one. Then he moves a bit the central atoms, and then he optimizes again the electronic energy. Then he get again the energy, then move a bit again the atoms, and again optimize the electronic energy. Okay? So now what we discuss is how they move from 1 to 2 to 3. This ionic optimization. There are different ways to do it. Okay? Yeah, so the mathematical problem is that we want to get the lowest energy configuration of a given structure. So that means that we need to go to the local minimum of a function. And actually, we would be even more happy if we can go to the global minimum. But the global minimum is something that we don't know in principle. So like all these algorithms go to the local minimum because it's the only way that you can approach. Now you don't know where the global minimum is. So, I mean, to do that, you know, like this is just like kind of quadratic equation, like you solve it as a parabola, nothing special here. I mean, a lot of formulas, but don't focus on the formula. And there are different algorithms, okay? The first one is the Newton algorithm. That is just an algorithm to try to get to the minimum, okay? So what this Newton algorithm starts is that you start in an arbitrary point. So this is your initial guess. This is the initial structure you give. Then you calculate the gradient of the forces in that point. And then it's telling you multiply with the inverse of the Hessian matrix and performance step. Like, let's put it easier, okay? Like, then you just like move. Performance step means that you just move your atom a bit, okay, in the direction of the gradient. So depending on how big is the step, and you tune the step with potting, your simulation will be slower or faster. But if you put potting steps that are too big, then you can also just forget or like skip a local minimum, because maybe you are moving from one like point in the parabola to the other one. Okay. Yeah. So you can see here like with this graph how this works. Okay. So for instance, this is telling you. Yeah. Okay. Initial guess. You calculate the gradient, and then you make a step. So you move your atoms. You optimize your position of your atoms in the direction of the steepest descent. That means basically that you move the atoms so that you minimize the forces, okay? Or you go in the direction that should minimize the forces. And then you repeat 2 and 3 until convergence is reached. And you set up convergence through a tag that is defined in VASP with add if J. That is basically like the threshold of the forces that you accept in your system. And usually we set it to 10 to the power of minus 2 volt to angstrom. Okay? Yeah, should be, or yeah, I think it should be that one. Well, 10 to the power of minus 2, and then like the units I don't remember properly, but we will check later. Okay.
Can you replace the command in the Inca?
Add if. We can actually maybe just open it. Okay. We can just open so that we can just yeah. So this is the command. Okay. Add if defines the break condition for the ionic relaxation loop. When add if is positive, the relaxation is stopped when the change of total energy is smaller. So we never use this, never. We always use add if FFG negative. So it stops when the norm of all the forces are smaller than add if FFG. Okay? So we always use it negative, and that means that when we get like when we have the norm of the forces in your system that are smaller than the threshold that we put in this parameter, then your ionic optimization is done. Otherwise, you keep having the ionic relaxation loop. That means simply that you keep having this. So here you got, it means that on the third ionic optimization, your forces went below your threshold. Okay, let's see if we set something here. Yeah, you see here, like we set a threshold of minus 0.01, and we can check what actually, because we have that, because you can actually see that. So if you go to convergence, you go to forces. Now we need to do it again. I mean, here you see that we don't really optimize much. Well, because this is way too big. But yeah, so the system here is basically already optimized. That's the reason why it doesn't really move. Okay, like the first one is already good. But so the forces are given in electron volt over angstrom. Yeah, because volt over angstrom are is the potential. And the force convergence happen when you have this energy that is going down. Okay, let's see if I can show you a different one of my standard like calculations so that we can see it better. So for instance, if I take one of them, okay, this one, okay, take this one, yeah. So for instance, in this case, should be if you got with forces, yeah. I mean, this is, there are not that many, but no, it's just here. Yeah, you see that this value is going down. And the threshold that we usually put is 0.05. So that means that when this line is going below, then your system is converged. Okay. So this is what we said. So this is this well, the tag that we just said. Okay.
But
yes.
Here, I think the more important one is the additive, immediate additive AG.
So these are two different parameters. The additive we will discuss later. Okay. The two different parameters are because one is this, and this one that I can open in a new window is the global break condition for the electronic loop. Okay. So coming back here, additive is the one that rules the electronic optimization. So rules when this electronic loop is done. Additive is the one instead that use the ionic optimization. So when 1, 2, 3 are done. So when the ionic steps are done. So both parameters are important because EDIF is the one that uses the electronic optimization. So if you don't have electronic optimization, then your system does not converge. But then also the ionic is important because if you are optimizing your system with, I don't know, two forces of 2 electron volt over angstrom, then your system is not converged. So both parameters are important, but we will discuss better the other one later. Okay, good. Then yeah, actually this will be the electronic optimization. Then we go back here. Yeah, like this is just telling you, okay, how many steps are required to converge to predefine accuracy. This is depending on like on your system, depending on how many forces you have. So if you have a crystalline system, usually after 10 ionic steps that converge. If you have like a semiconductor that is not well defined, it may take more time. But usually within like 100 ionic steps, you should get to convergence. So if you don't get convergence within the threshold that we set, means that your system maybe is fairly defined. Okay, yeah, like, yeah, this is just telling you like how like they reduce error. These are things inside the algorithm. I don't think you should focus on that. Not even this one. I mean, if you want, have a look, but I would not focus. Not even this one, because these are just like the things that rule how VASP calculate that, but it's not that important. Okay. Then, and this one, exactly this one, the one that we just said, like, let's say rule everything. Okay, so it's the basic one. Like it's the basic theory behind like the 2 Ibrio that we put. Okay, and then we need to decide whether we want to use Ibrio 1 or Ibrio 2. So if you want to use, whenever you put like Ibrio 1, this one, then you are using the, okay, sorry, okay, here, you are using the DISS algorithm. And if you're using the Ibrio 2, you are instead using the CG algorithm. Okay. And now yeah, like here is telling you, okay, if what I just told you determines when to terminate relaxation, positive values energy change between steps, negative value if the norm of the forces on your system is like below a certain threshold. Potim determines the step size. Okay. Now we will see like the theory, the formalism between this DISS, CG, and damp molecular dynamics. So what I just tell you since now is just what is basics like behind all the three systems. Okay, and now we go through CETA. So okay, theory. Okay, so the DIIS, that is the one that is behind the Ibrio 1 algorithm, apply the Newton scheme that we just defined. But in order to apply that, now it doesn't work anymore just with a point, it works with a set of points. And it looks for a linear combination between this set of points to minimize the gradient, okay? So it doesn't go anymore directly to the direction of steepest descent, so like to the direction of the gradient in order to minimize the forces, but given a set of points, like get to the linear combination and take this linear combination that can minimize the gradient. So like it's the same, it's just that it doesn't work with a single point, but with multiple points. So in order to see how it works, okay, we start again with an initial point, we take the gradient, we move along the gradient, so we go down, like we try to minimize the forces. Then in the new point, we calculate the new gradient again. Okay. Then we look, let's say, around the second point. So we doesn't look anymore in one single direction, but we look in a space around this point. And we look for the minimal gradient. Okay, so like, let's see if I can annotate, because I think it will be better explained. Okay, I think I should be able. Okay, but why this does not? Okay, yes. So let's say you start here, x. So this is your like xy, x1. Okay, then you go to a given position, x2, and here we are like here, okay, in the direction of the gradient. So that means that here you are minimizing your forces, okay? And now that you are in this x2 point, you don't move anymore just on a single direction. Let's say you have a space, so you need to think as, let's say, something like a space. So you have like some circles, let's say, and then what you do, you see different points around, you calculate the gradient to get to any of these points, and then you select the gradient that is the minimal one. So let's say you select the gradient that allow you to go to minimize at most the forces. So let's say if here the force is as minus 0.1 and here the forces are minus 0.01, and in all the other points, let's say they are higher than minus 0.01, well, plus, I mean, because the forces are positive, then you go to this point, then you move to this point, okay? Exactly, then you move and calculate the corresponding position. So then you move here, and then from here you keep the same scheme, okay? So then from this point, again, you have a space, you calculate the different gradients, and then you go to the position that minimizes your force, okay?
Sorry, but in that space, as I understand, there are infinite points. So you are calculating infinite gradients and taking the.
Yes, I guess so. I mean, I don't know. Like, I guess that like VASP set up an internal like,
Yes.
yeah, because you see this n.
What, sorry?
You see like the n here.
Yes.
So I guess, yeah, like the set of point probably something that is decided internally to VASP. We can check actually. Then so equilibrium. Let's see, because maybe there is a parameter. So equilibrium 1. Okay, I can also here alone. Okay, let's see equilibrium 1. Here, okay, and then to remove.
Excuse me, Federico, I have a question.
Yeah, go ahead.
I cannot understand the rule of equilibrium. What's this?
Of equilibrium 1, no? I guess. Okay.
I mean, the whole equilibrium.
Oh, okay. And I go through that. I just want to see that before. Number of degree of freedom is. No, I need to look better. So I will look better.
No,
but so for now, but yeah, there should be a, let's say, a limit now.
Yes.
Okay, so let's see. Okay, maybe here, yes, maybe this one will help us to understand a bit better in general. Okay, so we go through that. So you start at a given point, x0, okay, and then you go to okay, and then you have like a potem, so you move your atom, okay, so this x0 you need to think is about like the coordinates of a given atom, okay, let's take it simple like that. So you move this given atom in the direction of the steepest descent, okay, so you move it like to the position where you want to go, and then from this like xy, then you move in the space around, so you consider like different set of points around this x 1, you get all the gradients, okay? And now you move this point not for all the steps, but just to a given step that is the optimal one. So that is the one that minimizes the forces. So let's see if I can explain better by doing an annotation. So you need to think that like you set a optimum, okay? So you move from x1 to x2, and that is fixed. So let's see that you are moving it by 0.2 angstrom, okay? Then if you're moving it by 0.2 angstrom, and you get to this, what? Let's put it like x0 and x1, because then it's the same as here.
The 0.2, you are setting that?
Yeah, in the potting.
Okay, okay.
So in the potting, you're setting the step, okay? So, and you go in the direction of that minimizes the forces, okay? So let's say like the forces in x1 are lower than the forces in x0, so you go in this direction. But then the point is that since you get to the x1, you check around x1, so you check around this point, and you see if it's around this point, like there is any other point that minimize the forces even further. And in this case, you see, for instance, that like there is one point that is x1 optimal, and this point is at the beginning. So before, let's say, with your gradient, you would have gone here, but instead the optimal one is here. So let's see if this clarify everything. So what you do, now you need to think that like this is your optimization scheme, okay? So this is, let's say, your step, your potting. Let's call it step. How much you move your atom. And the y-axis is the forces. Well, the norm of the forces, okay? You want to go to the minimum, so you want to go here. So what it happens is that if your step is 0.2, let's say if you start from this point, then you will go to minimize the forces. But go to minimize the forces, if you have something like that, means that like you will need to go here, you will need to go here, you will go in the direction of the like steepest gradient, so you go down. But since you fix the step to be this, then you will move your atom here, okay? So this is x0 and this is x1. But this is wrong because you want to go to the minimum. Then after that, when you are here, like this algorithm, look all around. So look point here, 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 and adapt the step to go to the minimum. So you see that this x1 opt is the one optimized. So this will be x1 opt, okay? So that you don't go straight, you don't follow straightforward like the step, but you optimize the step that you are doing in order to get to this point. That is the point that minimize your forces. Is it a bit more clear now?
I mean, if we don't set a value for the potting,
there is a default value.
Okay, okay, the default. So the default one, what is it?
The default one is so potting. Yeah, now I need to clear all the drawing. Okay. So the default one is here. We did to desktop. Okay, potting. .5. Usually we use it like much lower, okay? So we use it 0.01, something like that. But you will get anyway the, let's say, you will get this value when you get a proper like project. Okay?
I mean, normally we get it for 0.01.
Okay, 0.01 then, yes. Then, this is the conjugate gradient, okay? So this is Ibrion 2. So the first step is the same, but then the search direction are conjugated to the previous search direction. So that means that now here you are saving some history, in the sense that you are remembering, well, VASP is remembering what happened before, and then is applying this knowledge to go for the next step, okay? So let's say first step is the same, so you move from, well, like here, you know, from x0 to x1. Okay. Then you calculate the gradient of the current position. You conjugate the gradient to the previous search direction. So that means that you combine the new gradient to the previous gradient. And you do a line minimization along this search direction, okay? So I think it's much better if you just check the graph. So as I say, the first things is the same. So we go from x0 to x1 straight. And then we check, okay, and then from here, you know, in this new point, x1, we calculate the gradient, this one, and then you take a linear combination between this gradient and this gradient to get to like the minimal gradient. Okay, let's see if I can, okay, yeah, if I can explain this better doing a graph. So as I said, like we have a system like that when here are the norm of the forces, okay? But you need to think that this is a simplification because this is a two-dimension graph, and in general what is happening is a 3D graph, okay? So what it means is that, let's say, like you need to think that this is something that can also be like 3D. So in reality, you have two directions, like, well, three directions actually. You go down always, but you can move in this direction, but you can also move like in this direction. That means entering the screen now, okay? So what, okay, so now let's, so if this is like the side view, let's now go with the top view. Okay, so below I will put a top view. So for the top view, we will have something like that. Okay, that is basically what you have here. Okay, so this is a top view. And you need to think that this point in the middle is your minimum, and you want to get there. So what will happen is that you will have the forces that varies in both directions. And now I change like the color, so I can put like the blue one. So you need to think that one gradient may be in this direction and the other, and you can have also another gradient in this direction. So what this algorithm is doing is like, let's say if the first like direction of the gradient was this one, and then from here you get like another direction that is this one, instead of going straight to this point, it takes like a linear combination that basically means like a sum, let's say, and goes then in this direction, okay? So let's say if this was your gradient at step 1 and this is your gradient at step 2, instead of going to this point, you will go to this point, because the algorithm will assume that this point is the one with the minimal forces, because it minimized the gradient in both the direction, okay? And instead, in this case, it just minimized one single direction, like the direction 2, let's say. Is it more or less clear? I mean, I know that is not, it can be not straightforward, okay? So let's say the previous step, the previous algorithm, the Iberian one, optimized the step in order to go to the minimum. Instead, Iberian 2, so the conjugate algorithm, what it does, it's simply like for the second gradient, it doesn't take just the second gradient. Take the combination between the second gradient and the first gradient. So like the new gradient that you calculate with the previous one. Because in this way, you can really go to the proper direction, okay? So it is a bit like if, think like, let's say, if you want to go, like if you have, let's say, a path and you don't want, yeah, and let's say if you have something here, you have like a wall and another wall, and you want to go, and the right direction when you want to go is the one in the middle. Like if you don't take, for instance, like linear combination, you will just of gradient, let's say you will just move from one wall to the other. So let's say it here, like for instance, if you start here, you will just escape from the wall, so you will go in this direction. And then if you go to this wall, you will want to escape, so you will go in this direction, and so on and so on. Instead, if you take the linear combination, so let's say if you start here and you go up here, and then let's say you will want to escape. Well, this is not the best way I could show, but let's say if you are here, then yeah, like then the idea is that let's say you take the linear combination, so now we'll be in the middle. I mean, the graph is not, let's say the graph is not that clear, but the idea is that then summing this and this,
to the other part.
you go here. Huh?
I mean the next part means outside the.
Yeah, like
yeah.
yeah, yes, exactly. Yeah. I mean, yeah. Let's see. Maybe I can make it better. Yeah. So simply let's say that whenever you take a linear combination of two gradients, then you go to the direction that minimizes both of them. I think is the easiest approach, and I should avoid keep talking about that because then I get more confused. Clear?
No, yes.
Okay. Okay. Then also read this because I mean it will help. Yeah, this is telling you how many steps you need to get. Then the third algorithm is Ebrion tree. Okay. So Ebrion tree is the one that, for instance, you may have used to optimize some bulk, or you will also use, for instance, if you calculate some transition state. And yeah, like it doesn't use minimization algorithm, but use a annealing algorithm, okay, that is called like damn molecular dynamics, okay? So it takes the position as the dynamic degree of freedoms. Yes, okay, then take forces as accelerations and apply the equation of motion, okay? And then use the Berlet algorithm, okay, to calculate the steeper descent step. So let's, okay, now, okay, so you need to take it as a rolling ball with friction. So let's say what it does, it's simply like you start here, okay? Then from here, it takes, like you have the forces, okay? And then you apply like the law of dynamics, okay? So the force is like your mass multiplied for acceleration, and it goes in the direction of the acceleration, okay? And you also apply a friction term in order not to have your like atom to escape, let's say, because if this is the direction of the gradient, if you don't have a friction term, then your atom will just go in this direction. But instead, let's say you move it, it goes here due to the friction. And then like from this point again, gradient in this direction. So it move a bit and then it stops here. And then again, same here, acceleration, well, forces. So acceleration in one direction and due to friction it stops here and so on till it gets to the minimum. Okay? Yeah.
I mean, in the Ebrion 3, they don't take care of the minimum energy in this case. So how if they don't take in account the
minimum forces. Remember that all these three Ebrion think about forces, not energy.
Okay.
So all the three look for minimization of the forces, like, but the first two, Ebrion 1 and 2, directly go to minimize the forces. Okay, so use algorithm that look at the gradient that give you the lowest forces. Okay. Instead, in this case, what they do, they don't take this gradient, but they just apply like law of dynamics in order to move your atoms to the place where the forces would like to move it. So if, let's say, better say, okay, like if, for instance, this one is here, the force of gravity makes that the lowest energy configuration of this bottle is to be on the middle.
Yeah.
Okay? Ebrium 1 and 2, let's say they calculate like the gradient, okay? Up, and for instance, they see that the strongest gradient in this case is for the bottle to be here, so they move it here, and then the same, and then the same till they get to the minimum. Instead, this algorithm doesn't calculate any gradient. They simply just open the bottle, open the hand, sorry, so it fell down. So law of dynamics, force equal to mass of the bottle acceleration, so it goes down. But then since they apply a friction, this stops. So again here they calculate forces, check the acceleration, let it fall, and it fell here, and so on. Okay, so they don't calculate anymore the gradient, but they simply let the system evolve as it should evolve due to the law of dynamics. Okay. This is more of a
that friction is something that you are fixing.
Yes, this friction is something that is introduced.
Okay.
And is given in this alpha here. Yeah.
Okay.
Okay. So it's basically like a term that is artificial.
Okay. Could you put the slide where the different Ebrium method? Yes. Okay. So maybe I know with smash. With what are you fixing with smash?
Yeah. Now we go to see what we are fixing. So I need to close this. So if we open now, well, we can open directly Ebrium 3. So Ebrium, well, we already had it open here. Then we go to 3. Damping factor. So smash is your is basically your yes, your like friction.
Okay.
Okay.
And the value that we should take for smash.
I need to check. I don't remember. Like, but like about all this like value, don't like write it now this down, because I mean they depend on the project that you will do and on your system. So when you will have your projects, then you will also have all the values you need. Okay. Okay. Yes. Okay. Okay. Yeah, so the set of point that you're calculating for this linear combination is set by N3. Okay, so what we were talking and discussing before, Enrique, is N3. So if we look for N3 now, this is so N3.
Sorry, but when you got that it's
yes. So so this is the number, like, so this N3 can be two things. Can be like the number of ionic steps kept in the iteration history. Yeah, so it's just that. Yeah. So yeah, N3 is just the number of ionic steps that are stored like in the algorithm that, let's say, use also the information about the previous gradient to get the new gradient. Okay. So that means that, like, if you get to 1003, it will remember all the 1000 like ionic steps that you had before. If you put 2, then it will remember just the previous 2, and so on.
Okay.
But if you don't put it, then you will just, I mean, VASP will just have his own guess. And then, okay, in the conjugate gradient, yes, they simply just go straight to the point. So, and they try to go directly like to the minimum. So here you don't really need to give any additional like information, because it will just fall directly to the optimization parameter. So like you will just adapt your potting.
So the one that uses the result the vector result between two vectors, it's the equilibrium one.
Yeah, so the point is that,
The
you know,
explanation that you did.
yeah, I fully agree. But I'm also getting confused now because the problem,
okay.
no, it's not you, you know, because the problem is that the way.
So n3 storing steps, it's about making that resulting vector.
Exactly, like that is also my understanding, but then here, okay, let's see. And if I cannot solve this now, then I will think about that and tell you tomorrow. Okay. This is. Yes, it seems so. Correct. Yeah, it seems that like they have mistaken the two, like the two things, so that these should be, yeah, the two graphs are different. Yeah, but it's better. I mean, I look about that myself, and that will not be surprising because the VASP has done all these answers are correct till a certain point, and then tomorrow I will just make a slide and edit myself with the clear differences because here it's not clear. I mean, it's clear that they are different, but it's not clear which one should be the different one. Okay.
Okay.
Uh,
the problem?
yeah, the problem is that according to the explanation, like everything, let's say, works till you don't get like to this slide, because then in this slide, like it seems that like the explanation that is valid for one algorithm instead should be valid for the other one. So there should be like a difference. But I will just like look for that. Yeah, also this one. Yeah.
And in your page, I think it's when the equilibrium equal to 1, the ion there is A0 plus A1 equal to 1. What does it mean?
Which page?
I think the equilibrium 1. A0 plus A1 equal to 1. The key points?
No, it's not key points. This is just like, yeah, this is just, I guess, the linear combination of the two things. Because, you know, this is just a sum.
But it's when equilibrium equal to 1, there is not the combine, no?
Yeah, yeah, but that's the reason why we are saying that, like, I need to go through this slide again because I didn't check them before, and I think it's not straightforward what they want to say. Okay. So just wait for tomorrow, and at the beginning, and we'll just prepare like a slide that summarizes everything clear, because this is not clear. They are missing a bit of things.
Okay, in the table, when to talk the equilibrium equal to 1, 2, 3, in the first part, they have said the other flag N3.
Yeah.
But the N3, we just use it when the equilibrium equal to 2.
Again, like here for this slide, no. But wait for tomorrow that I make a summary slide that is clearer than this one. Okay? Because like these things work, because also like in the online is like that. Okay? So basically N3 and POTIM is on 1, POTIM alone for equilibrium 2, POTIM and NSMAS for equilibrium 3. So this is the table, and this table is correct. Okay? But for the explanation of this table, wait for tomorrow, because then I will like sum up in a better way than this. Okay?
Okay.
Because also now to me is not clear. So yeah, this is just telling you like the other things. So like the different like parameter you need to set, but again, like you will be provided with the value, so don't worry too much about that. He's telling you about this tree, this quick min, and yeah, okay. So here is kind of giving some idea or what we should like, which system you should study. Remember that like the conjugate gradient is Ebrion 2, this Ebrion 1, and damped molecular dynamics Ebrion 3. Okay, good. Then here is just a summary or where you should apply each of the like algorithm, and this is the important slide. Okay, because this is just a rule of thumb of where you should use the things. So if you don't know much about your system, use Ebrion 2. If it's close to the minimum, so it's already optimized, so you just do a further optimization, then you have just few degree of freedom. So let's say like if you want to study absorption of a given molecule, then you can use like the Ebrion 1 as well. Okay, but also this table is not that clear. But let's say if instead you have a lot of vibrational spectra, so you have a lot of degree of freedom, then you can instead use Ebrion 3. But let's say like usually you start with Ebrion 2, conjugate gradient, and if you are close to the minimum or you are calculating absorption property, then you use Ebrion 1. Okay, Ebrion 3 you only use for bulk optimization or transition state. So this
Sorry, which one?
Ebrion 3.
Ebrion 1. Okay.
Transition state or bulk optimization. Okay, so in general Ebrion 2 or close to the minimum Ebrion 1. Okay, and here is telling you yes. Okay, this is exactly like, and here is telling you where Ebrion 1 fails. So for instance, Ebrion 1 fails if forces are increasing during the line optimization. So in this case, you see, for instance, that like you move from a position 0 to a position 1, but the red arrow is the arrow of forces, and you see that the forces increase along the line optimization. So in this case, like this algorithm, so Ebrion 1 fail because it will tell you, like in this case, like according to what Ebrion should do, like it will go to the other side, okay? Because you always want to minimize the forces, and in this point, in this direction, you have higher forces than this one. So actually, like if you apply Ebrion 1 in this system, it will come back here because it will try to minimize the forces, and in this point, you have less forces than this one. But actually, this is wrong because you should go to this point instead, okay? So that's why the conjugate gradient is better. Okay, and usually we use it. Okay, and yeah, this is just telling you that like is not easy, and that like is good to set like yeah, that larger system are more problematic because you have more things. Molecular system again, but again like this is just like general thing. So now we go very quickly on the electronic optimization that is easier to understand because I mean there are just a bunch of options. So, and again, like I'll go very quick on that. So this is what we have inside each of our system. Okay, so inside not zoom, but inside each of the ionic step, we do an electronic optimization. Okay, so this is to look for the electronic ground state, and there are different ways to do that. Okay, so as we say the first day, we need to solve the Kohn-Sham equations, and in order to do that, we need to sum the electron like charge density and also the kinetic energy. Okay, so in this, like, we need to account for the kinetic energy term, electrostatic energy, so the interaction between the electrons and the nucleus, and also like this exchange parameter that needs to be like assessed in different way, and here we have different like functional that can help us. So now what we are doing is just to solve Kohn-Sham equation to minimize the electronic density. There are different ways to calculate that. Like one is to go to the direct minimization of the functional. Okay, so if you remember, we said the other day that like the big two theorem in DFT say that there is a unique functional that you can solve, and that if you take the minimum of that functional, then the minimum of the functional like gives you also like the low, well, the electronic density that minimizes the functional is the electronic density of your ground state. So like one solution is just to minimize your functional, and then instead in the old fashion, you just go step by step. So what you do, like what you do is simply that you start with a trial electronic density, you set up the Schrödinger equation, you solve it, you obtain the one wave function. From the wave function, you calculate the charge density, and then if the charge density of your new like step is very different from the previous one, then you keep this process. So you assume this new charge density as the trial density, and you go on till you don't get to the electronic density that minimizes the functional. So that is the electronic density that should be the one that you have in your physical system. Okay. And yeah, like, and instead, like the previous case, that is the direct minimization of the DFT functional, just you start, instead of starting with a trial electronic density, you start with a set of wave function, and you minimize the value of the functional. So you get again to the minimum of that functional, and then from the minimum of the functional, you will have like the wave functions that minimize your functional, and from those wave functions, you get the electronic density. But this is just a small summary of what we have seen the first day. So here is just to tell you what we just said, that you need to minimize the functional. So you need to you need to get the electronic density that minimize the energy of your system, because you want to go to the lowest energy configuration. So you see here that like your energy is going down. So given the iteration, so given the optimization of the electronic configurations, you have forces and also energy that go down. Here, these one are forces, these one are energies, and here you see the different like approach. So the first one is the Carpar in yellow, so the one that start with the wave function and then minimize the functional, okay? And this one instead is the self-consistent. It is the one instead that start with a trial charge density, well, electronic density, and then you put it inside, you set up the Schrödinger equation with this trial electronic density, you get to a definition of wave function, a definition of updated like charge, electronic density, and you keep doing that, okay? So you see that like to apply first method or second method doesn't change much. You still get to the lowest energy configuration. And given like the different like system that you use, you use either like the Carpar-Yellow method, so the first things with the wave function, or the second one. But yeah, I don't think it's that important to focus for you on that, but it's important instead to focus on what is the scheme, because it's the important one. So you start either with trial electronic density or trial wave vectors or wave functions. You set up the Hamiltonian. Then you refine the wave functions in order to get to the electronic density or to the set of wave functions that minimize your functional. Then from the wave function, you get the new charge density. From this new charge density, you do optimization inside to get to the charge density that minimize your functional, so that minimize the energy. And then you get the energy of your system. And if the energy of your system minus the energy of the first step is lower than a certain threshold that you put with this like FDIF tag, then means that like your system is done, your electronic like loop is done, and so you can go to the ionic step. And if it's not, then you start again. Okay. So trial electronic density of wave vectors. You solve the Hamiltonian. You get the wave function. From the wave function, you get the charge density. You optimize the charge density. From the charge density optimized, electronic density optimized, you get the energy of your system. If the energy of your system minus the energy of the system before doing all these steps is lower than a threshold, means that your system is close enough to the lowest energy configuration, so that your system is electronically convergent, so that you can go to ionic step. Yeah, like algo is a parameter that you set in Incar and determines the way the wave functions are optimized. The only important like things that you need to remember is that usually we use algo equal to fast because it's the fastest one. Instead, if you change it, so you use it to, well, actually we even use very fast, I think sometimes. If you have problem with your electronic convergence, then you may use algo equal to normal. Okay, so that is the only important part that you need to remember. Then let's say behind this value there are different like optimization schemes, but it's not that important that you remember them. What is important is just to remember that like usually we use very fast or fast. I think the default is actually fast, but if you have, well, the default is actually normal, but so you need to set up fast or very fast because then your system gets faster. Will converge. Well, will not take that much time to converge. Then,
but there will be more error.
I mean, it's not that there will be more error. If you have a system that is a metal, there will be no error. So the problem is not about error, it's about electronic convergence. Because if, for instance, you have a very badly defined system, if you put algo very fast or fast, what will happen is that you will not get to your threshold. So that means that your electronic convergence will fail. And in case it fails, then you need to use algo equal to normal. So it's just about the speed of convergence. Okay, that if you use usually very fast and fast are good because they don't take much time as algorithm, but they are stable enough so that you can get proper results. But in case you have a badly defined system and you need to use algo equal to normal, that takes a bit more time, but it may be better for the electronic convergence. So like the problem there is just that if algo very fast or fast fail, so you don't get to the result, then you need to use algo equal to normal. But in case very fast or fast work, then you use both of them, and there is not a problem of what makes mistakes or not. Okay. Yes, you see, like generally a user cannot influence the behavior of this algorithm. So that means that like it's not that the choice that you do will change the final result. Okay, and here, yeah, here you see basically what is happening. Okay, so in the OTSI card, you see that we have in this case 7 electronic steps. We have like the first 4 of them, or 5 of them, are Bloch-Davidson algorithm. That in this case will be algo equal to normal, okay? And then you go to RMM. RMM would be the DIIS, okay? So it will be like fast or very fast, okay? And why this is happening? Because at the beginning, we want to have a proper, let's say, you start with the normal, because for the first 4 steps, you have your charge that is fixed. So you want to have a proper optimization of your electronic density, keeping like the charge fixed, keeping the electron fixed. And then from the 6th, you start moving your electron in the system, and then you start using the very fast. Because let's say you already have a good initial guess of your electronic density, so you can start moving them, and you will be able to go to the minimum, okay, of your electronic density and so of your energy. So this is just to, let's say, to say that usually in a OTSI card, you will see like 4 to 5 DAV steps. That means that you are using algo equal to normal, because you want to have a proper optimization of your electronic structure prior to moving the electrons. And then after that, from the 6 in this case, you will start moving the electrons. And in this case, since you already have a good initial guess, you can use the faster bet. Yeah, and he is telling you like the structure that probably you already have. So N is the iteration count, E is the total energy, delta E is the change of total energy, dx is the change of the eigenvalues, but this is not that important, number of optimization steps. Like, let's say these points are not that important, okay? What is important is just the iteration count, total energy, change of total energy. That is here. Iteration count, several iterations, energy, change of energy. So you see that at the beginning, like, we need to use algo because you see that the difference is changing crazily. So we are moving from a positive energy of like 483 electron volt to an energy of minus 34.61 electron volt. So there is a huge difference. But then you see that from the 6, well, actually from this case, the energy gets stabilized. So that the, like here, the difference is just about 0.9 electron volt, okay? Because here the electronic density of your system is already more or less converged. Okay, this is just a parameter. Yeah, this is just like about the theory that you are setting, but I don't think it's that important. Yeah, I will not focus on that. So because it's 11:33. I think what is important is just to go straight to the important part, that is, yeah, the real time. Okay. So as I said, like, if you have problem with electronic convergence, and problem with electronic convergence means that you are here, but you don't get to delta E that are lower, okay? So think that this delta E is always, for all your steps, something like exponential to the power of 3. So that means that your system is not going to the minimum of your electronic structure. You keep running and running and running, your electrons keep moving, but you don't get to the minimum. So this is a problem of electronic convergence. And in order to fix that, there are like 2 tricks. The tricks that I already said is to use the Davidson algorithm. So to put algo equal to normal instead of fast, very fast. And then if it converges, then you are done. You use this setting, okay? In case also with the algo equal to normal does not work, then you use I charge equal to 12. So that means that you are not anymore updating the charges, okay? So that means that you start with predefined electronic like density and you keep it, okay? If this, yeah, well, if this fails to converge, then like there is a problem with your system. And if like it does not converge, then you can also start playing with the mixing parameters. So the mixing parameters are like parameters that you set in the ink card in order like to tell VASP how VASP should optimize your charge update at the beginning, okay? So depending on how you optimize, you can get to have meaningful result or not. But again, don't focus much on this value because you will get this value. What is important for you to remember is that if you have problem with fast or very fast, you apply the normal algo, so algo equal to normal. And if you have problem with that, you start playing with these mixing parameters. But there is a very good page on our wiki where you get all the suggestions on how to do that. And it's not something that you will get to have at the very beginning of your system.
Normally I charge, we don't need to set.
No, normally you don't set I charge exactly. Normally, like the algorithm fast or very fast will be okay. And you set it to normal just if needed. Okay. Then, yeah, this is about like how the ab initio molecular dynamics work. But I think, yeah, skip this part and we will go through that next time, because also then we introduce the ab initio molecular dynamics. Okay, so I know that like today was pretty intense. Tomorrow I will prepare like 2 slides that I will give you after you read this one so that you can get more or less the important information. And now I just quickly introduce the hands-on 3 session. It's easier than the previous one, so it shouldn't take you too much time. And this is all about like optimization of surfaces and absorption energy. Okay, so you will have like 8 like exercises to do. You will find them on my Tekla home, hands-on 3. Some of them are complete, some of them are missing some input, and you will see why, because I mean, like in the next slide, I will say why. So, and what the studies that we are doing with this hands-on are the following, like, we are doing some calculation of surface energy because we want to calculate and to estimate the one that are the most stable surface facets, so the one that has the lowest surface energy. We can compare the surface energy that we get through VASP with the surface energy that we get with experiments. Again, we can check the band gap and the density of state of our like system. So here you see like these are like the 3 simulations that do that. We can calculate absorption energy. For instance, in this case, the absorption energy of CO on nickel 111. And we can also get the vibrational frequencies of carbon monoxide on nickel. Okay, so like this answer is about this. How you do that? The first things that you need to do, like, is just to calculate, to optimize, so just to generate your run script for nickel 100 and nickel 111. These are 2 different facets, cut in a different way. You calculate the surface energy applying this formula, okay? A is the area, and you calculate it from the lattice vector of your surface. Okay, you will see your surface. You will have like ABC, so the lattice vector parameter with x, y, and z coordinate. You need to multiply Ix per By, and you get the area. Then the energy of unrelaxed is the energy of the unrelaxed slab. So the energy of the first ionic step for your surface calculation that you can get with that. Remember always that is the energy for sigma that tends to 0. Then the energy of the last ionic step is E rel, and here you get it as well from the slab, but now you take tail minus N1 because you want to take the last energy because it's the energy of your surface when it's relaxed. Delta E rel is simply like the energy of your relaxed slab minus the energy of your slab unrelaxed. And then E bulk is the energy of your bulk crystal structure. So you will need to retrieve it from your previous answer, so answer 2. So 27 FCC nickel optimization, so the energy of your bulk structure. And then M is the number of unit cell in the surface. Okay, so let's say if you calculated the bulk with 1 atom, and now in these 2 surfaces you have like 5 atoms, this N will be equal to 5. Okay, and the question related to these 2 exercises are like, define or calculate the surface energy for nickel 100 and nickel 111. From this value, you will be able to define which is the most stable crystalline facet between nickel 100 and nickel 111, and the most stable is the one that has the lowest surface energy. Okay, you can compare the surface energy that you got experimentally for nickel to experimental values. Experimental values you will have just 1 for nickel, okay, because it's not that it's experimentally to get the surface energy of nickel 100, nickel 111. And then the last question, like, which facet is the most abundant on a nickel particle? Check the paper below to answer. Okay, so this paper is already on OneDrive, so you can just click here and it will open, and it will just tell you a bit about this Wolf construction. That is a formalism, a theory that is telling you that basically like the facet that has the lowest energy, the lowest surface energy, is the most abundant on a particle. And so that's why we calculate always surface energy before starting like any simulation, because the facet with the lowest surface energy is the one that should be more abundant. And then Anson 3, electronic properties. Here you will do the, what we already did in Anson 2. So basically, like, calculate the local density of state and the band structure for nickel 100. Okay, you will take the concurve from 3,1 nickel 100 clean as postcard, and for 3,3 nickel 100 clean band, you will take also the CG card. So the file with the charge density, okay, that you also have from 3,1 nickel 100 clean well, and you will also need to adapt the INCAR. So this is the INCAR from your 3,3 nickel 100 clean band system. You see that you have, like, on this line time some TBD, 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 and you will need to put, instead of this value, the 3 value that you see at the beginning of your CAG car file. Okay, so after you copy the CAG car from 3,1 to 3,3, you open it, for instance, with more, so with the command more, or with CAT if you want to print it. I mean, you need to see the first, like, 20 lines, and then you will see 3 numbers here, and you need to copy the 3 numbers here. So this will be 20, in this case would be 20, 20, 144 instead of TBD, TBD, TBD. Okay, and then the very last part, this is to calculate the the absorption property of CO on nickel. So 3,5 and 3,6, you calculate 2 energy. One is the energy of your carbon monoxide on top of nickel. The other one is the reference energy, so the energy of your nickel alone. And then in order to calculate absorption energy, you take the total energy, so the energy, the last energy, let's say your final energy. So graph energy, space W, outcar, tail -1, because you want to take the last one for sigma that tends to 0, minus the energy for your clean system, so the 3,6 simulation, minus the energy of your carbon monoxide alone that we calculate in the first Anson lesson 150. Okay, so you should get a value that is in electron volt, and this value in electron volt is the CO absorption energy. So the last question will be, how much is CO absorption energy on nickel 101? And again, compare with experimental values. And experimentally, you can get the value with, for instance, thermal desorption spectroscopy. Okay, and oh yeah, the very last part, you will need to calculate also the local density of state for the carbon monoxide, and most importantly, the frequencies of your carbon monoxide on nickel 111. So in order to do that, you will need to take the concurve from the simulation 3.5 and to use it as a postcard. Okay, and then when you are in the simulation 3.8, carbon monoxide on nickel 111, you will need to fix the coordinates. So let's say after you copy the postcard from the 3.5 simulation to the 3.8, then you will need to open, like, the postcard on the 3.8, so VI postcard, and to make sure that just the Z coordinate of the carbon and oxygen atoms are free to move. So basically here you will just calculate the vibrational frequencies for CO stretching, okay? Because you will just let your carbon monoxide move up and down, up and down, up and down. Because the only coordinates that are free to move are the Z coordinates of carbon and oxygen, of the carbon monoxide.
Why not just take the CO and in another box and doing this?
Yeah, because you want to calculate the CO stretching frequencies for CO on top of nickel.
But the other atoms are fixed.
They are fixed, but CO still feel that nickel is there.
Okay.
So you see, like, in this case, you will just get the CO stretching frequencies, but that will not be the same CO stretching frequencies that you will get for CO alone. Because in one case, in the box, you have CO alone, so you have a floating CO as a gas, and in this case, you have a CO that is absorbed on nickel, and so there will be some interaction with nickel, so the stretching frequencies will be different. Okay.
What is the utility of the 3.7 simulation?
The 3.7 simulation, you will see it in the Anson 3. I didn't really focus on that because, I mean, personally, I don't find it very, very relevant. But the utility, I mean, there are two kinds of utility. So one of the utility is that, yes, you can see the local density of state. So in this case, you can split by, okay, now I put it like a presentation. Okay, so you could see the overlap between like the different density of state. Okay, so for instance, you can go to band control, and now we are going to do it like in a second. I will just open like the things that I already do. And you can see how, like, for instance, like the D band of nickel overlap with like the P, or well, sigma orbital of carbon monoxide. And so if there is overlap, means that there is interaction. So you check this kind of things mainly if you want to see which kind of hybridization is happening there, which kind of interaction. And then the second thing that you also will do is also to get the work function of your system. Okay. So, and now we will just very quickly, well, very quickly, we still have time, so I will just show you what I meant about these last two parts that I did just ask. So, okay, a bit slow, eh? So let's try to open a new terminal. Okay. No. I need to open a new, I think I need to open again. Okay, so terminal 1. Terminal 2. And then and then I zoom. Okay, so now you will have this calculation. Then if you open the VASP run, you can go to structure. You see the structure here. So the system is basically a nickel 111 with a CO on top of one of the atoms. Okay, if you want, you can also like multiply just to see it better. You see like that the coverage is rather high because you have one CO molecule for every like nickel atom on top. Okay, so this is a really, really high coverage. And you see, for instance, that the distance between this nickel atom and the CO, if you want to see the distance, you can go to structure, measure, is 1.75. So before I was telling you that the distance for the script should be 2 angstrom for the reason, okay? So like here you go to electronic and you can go to local dose plus band control, okay? So this is the density of state of all the atoms that you have there. For instance, if you go to like, if you select just, well, let's select just the carbon. Okay, in this way, we just selected the carbon.
Which command are you using to select atom?
To select atom, you need to put your mouse on top of the atom, and then you put like the space bar.
Okay.
And you just click it, and you know, like now it's selected. I mean, it's not easy to see, but it's still selected. And you also see it here. Or the other thing that you can put, you can just put like in selection, you put C. Okay. That will work the same. So CO, for instance. And now you go to the panel that we had before, so this one, you see that it's like atom selection. Then we can put like P, we can put SP because we want to see the SP like orbital, and then you do select all of them, and you select all the S and P orbital. Okay, so now what we are taking is just the SP like band of the carbon monoxide. And now we can put like line, this one it's okay, symbol, we put, let's put it blue, and add new line. So now it's not that easy to see, but I can zoom in. Yeah, you see that now here, this is the line for your SP. So this is the line of your sp orbital, okay? This is the line of your carbon monoxide. And now, if we want, we can go instead for the D of all the nickel. So if you write, if you provide nickel, then goes to all the nickel. Or if you prefer, we can just deselect and we can just take the top nickel atom. So that you see that here we have a number. Now we can put like D nickel, and we can put as line something that is different, like orange. Okay, just at the end, then we add the line. Okay. So now, so now you see, for instance, like what we have here. Let's just focus on that so that is clear. So now you see that this blue one is the S and P band of your carbon monoxide. The orange one is the D band of your nickel. So since they overlap, there is an interaction. That means that the CO is absorbed on nickel. Okay. So you play with that. And the other thing that they will also ask you an answer is instead to go to local potential. Okay. So this local potential is the, let's say the potential that you have inside your slab. Okay. So you can go to show to the different directions. So this is X direction, Y direction, and Z direction. Okay. So just to clarify it a better, like Z direction means this one. Okay. So you see like this oscillation because you see a minimum whenever you have an atom. So this is the first nickel atom, second nickel atom, third nickel atom, fourth nickel atom, fifth nickel atom. Then these two minima here are for because we have the carbon monoxide. And then this one is actually like, well, it's not your Fermi, it's your vacuum energy, like it's your energy when you don't have anything, you know. So like in physics, for instance, the way that you define the ionization energy, yeah, it's, well, no, sorry, let's go better just on the file because now I'm making confusion. Okay. So you know that in physics there is like a definition that is the work function. Yes, the work function. Okay, let's make it better. Yes. So the work function in physics is defined as the minimum thermodynamic work needed to remove an electron from a solid to a point in the vacuum immediately outside the solid surface. Okay, and the way that you calculate the work function is just like taking the electrostatic potential in the vacuum nearby to the surface, and EF is the Fermi energy. Okay, so the electrostatic potential in the vacuum is this value, and your Fermi energy should be here because the Fermi energy is in the middle, like, of your nickel. So the work function is the energy required to move one electron from this to this level. So to move it from your surface to the vacuum. And you actually will have, exactly, you will have like to calculate the work function. So you get the Fermi energy from the outcome. Okay. So in order to get it from the outcome, we will do it later, but there is a graph like functionality to do that. And then the vacuum potential like is this value here. So in this case will be something like okay, now let's see why I cannot. Okay, now yes. So this will be your value. For me is around 5. Okay, and then okay, vacuum potential you have, and then like you just need to apply this formula. Not this one, sorry, but this one. Okay, yeah, this one. So like the phi is what we have, E is the charge of the electron, and EF is your is the Fermi energy that you get from the outcome. But I think there are the explanation on the answer. Yeah, it's telling you. This is just telling you that you should look for density of state, and then from here you can calculate the vacuum potential, 649, and then like you can calculate the work function if you want. Okay, with this equation. Now you just need to type work function on Wikipedia and you will find the things. And in order, just the last things, in order to get the work function from the out card, we did it the other time, but you need to type like red. I think something that should be this. No. Yeah, you play a bit with that. Okay, so the Fermi energy is 1.67.
You can also extract the Fermi energy from the Oscar, right? Because yesterday we saw.
Yeah.
Ah, yes.
Yes. I mean, in general, I think. Let's see if we open again the VASP run, then you go to those plus one. Yeah, I think it's somewhere here. I mean, it's not easy now to check it because it's like, well, this is a mock.
It's exactly where in the zero, the Fermi energy.
Yeah, like automatically they shift it to the zero. Yes, indeed. Okay. So it's not really helpful, but still, like I think you can do it from the DOS card.
Yeah, we checked that. 1 point.
Yes, exactly. Yeah. Yeah, because you see that. Yeah, you see that you have other energy here. So this is like the real energy you have. No, actually, I think that this is already shifted, probably. Yeah, they already shifted, and that's why they are telling you at the beginning, which is your reference number. Yeah. Okay, good. So, yeah, I think if there are no questions, we are done.
The first 111 you have cut it better.
We have cut it.
The first nigger 111 that you have cut it yourself.
No, it's already done by the Anson. I mean, all these input that you're getting are given in the Anson package.
Okay.
In the future, you will need to cut them yourself. Okay. So for next week, when we meet, like this will be the 3 questions that we say. And at the end of this presentation, you also see the standard like suggestion how to do so. Open a terminal, establish a connection, copy the Anson tree from my like Tekla home, entering, checking the in card. This part here is in blue, is not that visible because it's only for Mariam at the beginning, because I assume that all of you already like change the Rangen and your bin. And then in your case, instead, you will just need to generate the run file on each of these folders, and then you submit them, okay? And you do the things that they ask in Anson tree. And then tomorrow we discuss potential doubt that you have. You can bring your own computer. We also go through like the Python script that is missing for you. So the one about like the absorption on top. And I will also prepare 1 or 2 slides to summarize much better than like this Anson, like the different algorithm that you have for the ionic optimization. Okay?
Okay.
And and I think it's all for today. If there are no questions, Mariam, everything is good? You're still alive?
Yeah, thank you. Yeah.
Good. So,
Thank you very much, Federico.
Yeah, no worries. And as I told you yesterday, Mariam, start with this one. Don't start with this one, run this one, and then slowly you go back to recover the 1 and 2. Okay, not to add more. Okay, because
so for comments that I don't know how to run them, I should just Google them. I mean, something like that, because it's my first time. So yesterday I tried to do the first one, but it wasn't that much clearer for me.
Yes,
that's why I'm asking.
It depends. So for the VASP, yeah, like in general, like all the commands, also this one, you can just Google, putting bash in front, and they will tell you what you are doing, okay? And also recover all the previous 2 slides, because in the previous 2 slides, you have a bit more like explanation of previous steps, okay? So even though, like, as I told you, focus on the 3-1, but still check the slide of the first one, mostly like the last slide, you know, like this one, where I go step by step. Like, for instance, here I'm telling you, okay, to make a directory is emptier to copy exercise the CP, because then you get the important comment that you need. And instead, if you are missing some like input from VASP, yeah, then you need to open the VASP manual online, and you can just copy some of the tag that you have in the Inker and understand there what they mean.
Okay, thank you.
And then, yeah, like, send me email if something is still unclear, and still, we will see each other tomorrow. Good. Good. So if we are all done, then thanks again for your time, and we see each other tomorrow. Okay? And I will be in the office today for you. So if you have any doubt, anytime today. Now I'm back to normal life. So bye, Mariam.
Bye.
Okay, stop here. Stop recording.